screen.
Yeah, thanks, David. Can you still hear me?
Yes, can you hear me?
Yes, I can. Okay, yeah, I'm just going to just say a couple things up front and then let David Sicarni present the findings of the research. First of all, if you would like to get professional development hours certification for this meeting, just email me at the email that's in the invitation and we'll get that out to you. I would like to recognize the Technical Advisory Committee that helped guide this research. Every research project has a TAC, and this one consisted of the following people: Jared Esselman, who was the project champion, Paul Dameron, who's also with aeronautics, and I see he's participating. Hi, Paul. Chad Worthen from WFRC, Adam Robertson from Fordham Tech, Brent Eliason from the University of Utah, and Rudy Zamora, who's with the Department of Technology Services, who sat in as well. The work was completed by a research team at the University of Utah that consisted of David Sicarni, formerly of the University of Utah, now with Blyncsy. Also on his team was Kathy Liu from the Civil and Environmental Engineering Department, and Thomas Henderson from the School of Computing. So with that, I'm going to sign off and give the time over to David, and we'll have time at the end for any Q&A. Thank you.
Thank you, Bob, and thank you everyone for joining. This was a very fruitful project for our research team, and we appreciate UDOT's sponsorship to accomplish it. So just jump in here. So a little background on the motivating problem, and please, anyone, you're welcome to ask questions. I know at the end we'll leave some time, but you're welcome to ask questions during the presentation as well. So advanced air mobility references a general mission to help emerging aviation markets safely develop an air transportation system that moves people and cargo between places previously underserved by aviation. And it uses revolutionary new aircraft that are only now just becoming possible. One of the major hurdles is automating air traffic control. And one of the sub-problems to consider within that is how to detect anomalous flight operations. So this is the main subject of this project. And you can see here I have a video of Blade Runner, and you can see these flying cars kind of swerving through all of the buildings. You know, this was really what was in our mind when we started this project was, you know, how would this actually work? And you know, what is the role of you know, local government and federal government and all, and how they're going to control this aspect of this new transportation system. So the main project goals, we wanted to look at the impact of different virtual highway configurations. So just like in that Blade Runner video, you have all of these basically virtual highways that weave between the buildings. And so we designed these virtual highways and said, you know, what are the different aspects to consider when you're building these things. We looked at the impact of tactical contingency response. So if there is an issue and the aircraft cannot follow their intended trajectory, what is the effect on the total system? And we looked into an investigation on trajectory anomaly detection using this what we call the lane-based approach. So once you have this system going, how do you know that it's operating correctly? How do you detect problems? And then, you know, how do you classify those problems? You know, is it a normal issue that's related to normal operations? Maybe it's a weather event, or is there something actually wrong with the vehicle, or has the system been hacked? These sorts of issues. Some more background on where NASA, the FAA, and industry are on this problem. So in 2019, NASA published an RFP looking for industry partners to collaborate on airspace simulations and software development. And we were actually working with UDOT at the time. Our research group was invited to working group discussions at the aeronautics department. And so what, you know, I wanted to make sure that we had all the information. And so I started a company called Geot and applied and was accepted into this Advanced Air Mobility National Campaign. So we became acquainted with the state of the art and discovered, what their proposed system was for coordinating airspace access, which turned out to be fairly complex, and I'll describe it in a minute. And it really made it difficult to understand in any cogent way what the airspace was supposed to look like, or predict what the behavior of the system would be under different circumstances. And these were exactly the questions that were being asked at those working group meetings. We wanted to know how many aircraft we're going to fly, we're going to be able to fly, where do we put infrastructure, what is this system going to look like, and then how do we control it? How do we make sure that we maintain accessibility for the vast majority of people, and it's not just a thing for people who can afford this type of new transportation system. So we wanted to be able to answer all those questions, and it seemed like, at least from an engineering perspective, what was being proposed by the government was too complex to be able to answer those questions. So underlying the proposed system for coordinating airspace is a concept called strategic deconfliction. Basically, before you fly, you have to make sure that your trajectory is conflict-free. So here's an overview of how this proposed system functions. So imagine a UAS, unmanned or uncrewed aircraft system, would like to plan a trajectory through the airspace. To ensure that its flight does not conflict with any other aircraft, it must reserve the airspace along this trajectory. So first, it takes the airspace and it takes the trajectory and it makes blocks out of it. And these blocks are defined by a square or any sort of polygon in 2 dimensions, and then an interval in altitudes and an interval in time. The UTM architecture, and UTM is the UAS traffic management system. This is what's being proposed by NASA and the FAA. The UTM architecture has a number of delegated authorities which are approved by the FAA to reserve airspace. These are the UAS service supplier for small UAS under 400 feet altitude, or a provider of services for urban air mobility, or PSU, for UAS operating in airspace over 400 feet. I'll use the two interchangeably because really they are derived from each other. They are being developed in parallel, and they share a lot of similar aspects. So you want to reserve this airspace. So the operator contacts its associated USS, which then contacts a discovery service. The discovery service is, let's see if I have it here. I'm not showing discovery. Oh yeah, discovery service on the left. The discovery service is it maintains a database that divides the Earth up into what are called S2 cells. And you'll see the little depiction there on the right. And it enables the USS or PSU to look up any other operation that may pose a conflict, one that you might run into given your proposed trajectory. If a conflict exists, the operator must contact the associated PSU USS of the other aircraft and request all of their reservation volumes in that cell of interest. Okay, so then once that happens, the operator is responsible for deconflicting its proposed trajectory with every other proposed trajectory. So you can see it's a fairly convoluted process. A lot of this seems to come from the want or the desire to have these delegated authorities, these like approved entities that allow this air traffic control coordination to happen. It's a kind of a replacement for human air traffic control, right? There's no tower in this case. There's just some system that allows this coordination to happen. So there was a lot of things that they were considering, and what we ended up with was a rather complex system, one that's very difficult to answer questions like how many aircraft can fly at the same time. What is the airspace going to look like? And so that's what we're trying to address. So the dimensions of each of these reservation volumes that I mentioned, you have to chunk your trajectory, and the shape of the collection of them is really at the discretion of the operator. And that's, again, one of the reasons why this is very difficult to tell what is the airspace going to look like, because this is not like a standardized process. It's not. You can choose a very small number of or small volumes so that you can approximate some very curvy trajectory, or you can do big chunks that essentially reserve the entire airspace for all of that time that you're flying. And so that's a very inefficient way of doing this. So it might make sense for, say, hobbyists or inspection applications where you would reserve, say, a large volume around a bridge or something. But for transportation, it doesn't really make sense. It's like if you were to get up in the morning and you wanted to drive to work and you reserved all of the roads that you took to work and for the complete amount of time that it took you to get there. It just doesn't really make sense to do that. It's not very efficient, and there's no rules about how you would do that sort of reservation. So here's our solution for controlling this autonomous air traffic system. We structure the airspace by a network of virtual lanes, which are three-dimensional structures that constrain the possible paths through the airspace. Trajectories are then reserved according to a common algorithm, a common recipe. This combination of features makes the overall system behavior much more predictable. We can interrogate the airspace using tools from ground transportation, which is one of the main inspirations for this type of system, and tools like network analysis, rather than simulating, an endless number of possible trajectories and collections of trajectories, which is what the current system would need in order to answer any of those very simple, straightforward questions. So the idea of this lane-based approach came about during those working group discussions that I mentioned before, that began in the fall of 2018. The director, Jared Esselman, brought up possibly restricting low-altitude UAS to the airspace above roads for a number of practical and political reasons. Additionally, many questions were raised about how many operations could be supported and all of those things and what infrastructure was required. So to me, it was clear that these questions had to be answered somehow. And one of the ways to make this possible was to structure the airspace in this way. And this depiction here was actually produced during that working group, those working group discussions, I believe, by Jared. So we took that, and we were really inspired by how ground transportation works, which is it's fairly efficient, and one of the main features that we were looking at was roundabouts and signalized intersections. So to coordinate airspace access is kind of the same problem. You can't have two cars in the same place at the same time, right? That would cause an accident. And there are a couple ways of coordinating that access. You can create a signalized intersection that makes sure that only one vehicle is passing through that intersection at a time. And of course, that takes some complicated equipment, and it's fairly expensive. And alternatively, you could build a roundabout. And for reasons that maybe are not too obvious, a roundabout does not need a signalized intersection. Doesn't need any traffic operations. Really, the people that are entering and exiting the roundabouts are able to make these decisions without much work, right? It doesn't take much effort. You're just looking in one place to see where that vehicle is going to intersect, and you can say yes or no, I can go or I can't, right? So the idea was, let's try to reduce the problem of coordinating this airspace access by kind of taking inspiration of these types of intersections that don't require all this heavy external equipment to coordinate that access. So we call this the lane-based approach, and it addresses several of the underlying problems with the current approach, those being inefficient airspace usage and deconfliction, and unpredictable trajectories. So on the left side there, you see those kind of things that I mentioned. And then in the lane-based approach, it's all predefined, where you can fly, where you can go. It makes it much easier for computers to make decisions. And at the same time, it also makes it easier to interrogate what's going on in the airspace. We have these very efficient diagrams we call space-time diagrams. They're used for ground transportation engineering, and we are, I believe, the first to apply them to an airspace coordination system. So a little bit more about what these lanes really are. We maintain minimum separation between aircraft in the direction of travel, and that's specified as a headway distance, same as for ground traffic. And that's a parameter that can be both individually specified by the aircraft if they need, they have hazardous materials and they need extra space, or they're a slow-moving aircraft or they're having an issue. But it could also be specified by governments, regulators. So this was one of the main reasons why we thought this would be a system that we could use to answer a lot of these questions about airspace access. Obviously, if you increase the headway distance, then you decrease the number of aircraft that can fit in any given volume. So you have some control over what is the density of aircraft in the space. And then in the other directions, we have this 3D volume, and so the lanes actually modulate the space in between aircraft side by side. And this may not be too important to those in the audience, but at least for the software that runs on these aircraft that have to make the decisions about where to go and how to get there. This is called a motion planning problem. What we've accomplished with this system is that the motion planning problem is very easy. It's extremely easy. And alternatively, with NASA system, it's extremely hard. And it can take an unknown amount of time to solve. So we were really trying to solve multiple problems here, make it easy to write the software that could go on these aircraft as well. So the steps for strategic deconfliction, which again is determining, before you fly, before you take off, am I going to run into anyone on my proposed flight? The steps to figure that out are very simple. First, you choose a path, and you reserve the best launch time, and then you reserve the launch time that you'd like. The system will then let you know when you can go. So, and choosing a path also gives you an opportunity to provide other services. So there's a lot of industry abilities that could be pulled into this type of system. So I mentioned that we took a lot of inspiration from roundabouts. I'll talk about that a little bit more. But these lanes give us the ability to think about a lot of different problems. Like, for example, we can create priority lanes for public service. We can create special use lanes for contingency handling, like a shoulder on the road, and also this lane-based system does work within the NASA model. So NASA's model allows you to reserve a big slice of the airspace. So we can reserve a huge slice of the airspace, and then within that, do this type of scheduling. So we're not trying to, throw away all of the work that they're doing here. We just want to be able to answer a lot more questions about how things are going to work within that system. So the standardization of lane systems can function similar to road networks. So that makes the system more simple. It makes it easier to analyze. So, as an example here, this is the FHWA standards for entry and exit speeds at roundabouts based on their geometric properties. And they make assumptions about, the turning radius, the capabilities of vehicles. And we would do exactly the same thing for the air. So we would say this slice of airspace is available to these types of aircraft, and these are the standards for how this type of system can be designed. And you can see here I have a roundabout for which we've planned a trajectory through using some real simulated trajectory algorithms that are used for aircraft. And so you can see it has a nice curvy shape to it. but it still fits within that the standards that are set. We've done some work in constructing different lanes, so lane systems, I should say. So here's an example of a lane system over San Francisco. We did 2 altitudes here, so they travel in 2 directions, and then we have these roundabouts that are at intersection points. We've also looked at single altitude lanes. It presents different types of issues there because you can't get everywhere unless it's a certain type of network. And so we've explored the single altitude lanes as well. We've done some development for these prototype systems in Dubai, where they were testing some a volocopter system there. And so it's easy to say, hey, where are they going to fly? We'll design a lane system, and here's how you use it. Here's a simulation for a lane-based system over Salt Lake City. And we constructed this using a particular kind of network. And you'll see later we're looking at different types of structures and how they affect the resulting system. What we did here is we sampled ground locations. And we said we're going to make those land and launch sites. And then from that, the system automatically generates that airspace system. And here you can see these kind of white hang gliders represent UAS flying about 400 feet above the ground to and from those locations. And they're scheduled according to that 2-step simple procedure that we described earlier. The interface that you're seeing here was developed as part of this this project, with the sponsored project by UTRAC, and we're continuing to develop this interface. So a little bit about the structure and the comparisons of different structures that we looked at. So the nice thing about this lane-based system, where we predefine all of the possible routes, is that it supports an analysis, before even simulating it. You can tell certain things about how the system is going to behave just based on how things are connected. And so we looked at a couple different things here. As an example, we compared it to, say, this kind of free flight model that FAA and NASA are proposing, which is basically as the crow flies. Everyone flies, straight shot to where they want to go. And we looked at that in comparison to a number of different spatial networks. So it turns out that these free flight as the crow flies type models, they create congestion points kind of in the center of these like density zones. So wherever things are trying to cross. So if you were looking at an urban city, and say a lot of the vertiports were outside of the city, and some were on top of buildings, for example, you would find that there would be congestion points. Even though there aren't roads up there, there would be a lot of conflicts that were generated, say, in the center of that. And so, you can't have, there's no way to control that given the current proposed system. But with the lane-based approach, you can say, okay, we're going to separate this, and we're going to kind of move traffic around in this area. It's kind of like, just imagine if you could take our current road network and you could instantly redefine how they are connected. Obviously, that would give us a great deal of control over traffic situations. So it's the same idea here. We looked at some other spatial network measures that give us an indication of whether there's going to be congestion in a given area. I mentioned before that we were able to take the ground network underneath and actually create an airspace structure from that. And you can see that in the bottom right graph there. It's actually a depiction of an area in Salt Lake that we tested. And if we just took that network as is, there are certain areas that would likely experience more congestion than others. And that's just based on how the network is structured. So how do we like measure, what are the things that we're interested in about these networks, and how do we measure them? We came up with a couple of measures that we wanted to use. So first was this failed flights measure, which is like a canceled flight. So you go to the airport, and for whatever external reasons, weather or whatever, you're not able to actually take that flight. It's canceled. You have to go home. that's a failed flight. These failed flights in the simulations that we do are associated with the congestion itself. So if an aircraft cannot get a path where they want to go at the time that they want to go, then that is considered a failed flight. Then there is a delay, which is the amount of time between when you want to launch and when you're actually allowed to launch, based on the amount of traffic that there is. And then deconfliction time is a measure of how easy it is to compute your trajectory. So in the NASA system, for example, I mentioned you have to deconflict, check every other trajectory before you take off. It's like getting up in the morning and looking at Google Maps. You want to go to work, and you have to basically register with every other person on the road and make sure that they're not going to cross your path at the time that you're going to be driving through. So you can imagine that gets harder and harder as there are more people on the roads. It's the same with, it gets harder and harder when there's more aircraft in the air. That is a measure of deconfliction time, is that kind of effort that's required. We looked at a bunch of different combination stuff. So we ran, hundreds and thousands of simulations, and we gathered statistics on these things, and we measured, we changed the parameters. So these are actually, a lot of these parameters are things that, say, a local regulator, UDOT Aeronautics, could set for a specific area. So some of the things that they could set, for example, are the speed limit, and that's the green line. The headway distance, which I mentioned before, is the spacing between vehicles, and then a flex time, which is more of an individual measure. It's like if you want to take off at 12 p.m., how flexible are you on that time? Or are you willing? Could you take off at 12:15? Could you take off at 6 p.m.? Right, that's the flex. So we modified all these parameters to see how that affected the system. And actually, what you're seeing here is every combination of those three parameters given a couple different values that we added there. And I'll just give you kind of the high level here, but essentially for failed flights, some of the systems performed better than others based on how they are structured. And one of the examples is if we took San Francisco roads and we just lifted them into the air and we use that as a system, well, that doesn't work very well. That actually is very sensitive to these parameters. If you change, say, the flex just a little bit, everybody gets canceled. If you change the speed just a little bit, people get canceled. And a similar thing is true with the FAA model. So we tested this FAA model, we simulated that, and you can see this large blue spike is basically showing you that all of these parameters affect those systems more. And so you're less certain about how that system is going to behave in any given environment. We have to make all sorts of assumptions about what the vehicles, where they will be going and what they will be doing. Whereas with all of our system, all of our networks that we intentionally designed, they are much more robust against these parameters. They will still allow a lot of different things to happen, which means that you could, for example, in the case of say some weather events, local authorities they have some new sensors and they can tell that there's going to be a huge gust of wind through Emigration Canyon. Well, let's increase the headway distance of all of the aircraft. Well, how much do you increase it before you cause a problem? You would, if you increase that headway distance just a little bit for an FAA type system, well, that's going to have a huge effect. People are going to get dropped, their flights are going to get delayed, all of these things. With our system, however, that's not necessarily true. You would have more flexibility in setting those parameters. We looked at delay as well, and it has a similar response. You get a lot more delay when you change those parameters for certain types of air networks. San Francisco is pretty bad, just given their road network. I think it's very dense and has a lot of choke points. And the FAA system also had similar issues with delay. And deconfliction time, of course, as we said, our system will perform a lot better You know, and you can see just how easy it is to schedule something in our system as opposed to the FAA model, which is very complex and it grows exponentially with the number of aircraft that are in the air. So overall, you know, low flex. So if people are less flexible with their times, low speed, so everyone's flying slowly, and high headway means everyone's spaced apart. That means you're going to have less airspace capacity. And as I said, the FAA and that San Francisco model are most sensitive to that, but many of the other systems are not. A little bit about contingencies. So contingencies are unplanned events that you have to you know, plan for now. You know, this would be, for example, a system failure on your vehicle, or a gust of wind. These are all contingencies that were unplanned for, and so you have to do something, and it's going to affect the system. And we came up with a recipe for dealing with those types of situations. Again, our goal was to make it as simple as possible, so we could, you know, implement this in a couple lines of C++ or whatever the code on that system is, and it would perform as expected. It's not a giant, you know, coordinated effort. Basically, you're going to be looking at the aircraft in front of you. If you're unable to get communication systems, you'll use your sensors, and you'll say, hey, am I getting too close? And you'll slow down. And the way that you slow down, you have to communicate that to other aircraft. And if you do what we say here, then it's a pretty stable system. It will be able to deal with a fair number of contingencies, and the intensity of those contingencies. Another thing that we looked at was the monitoring of the airspace. So, you know, the air traffic controllers, they have the ability to use radar and these types of systems, and you can also set up ADS-B, which is many aircraft, at least commercial aircraft, are required to, but many aircraft have these transmitters that will transmit their location at once a second, and you can put a radio on your roof, and you can see all of the aircraft, all of their positions flying over your house. So the question, though, is, could you use all of that data and tell when something's wrong? Well, if you have all of the trajectory information, all of the intent, you know, the operational intent of those aircraft, then it may be possible, but it's difficult, because you have to then, again, compare all of this information. There's a lot of data to crunch there to figure out whether something's wrong. Well, with the lane-based approach, we have a system that we've predefined. We predefined all of the areas. And so that's basically a model of what the airspace is supposed to look like at any given time. And we can use that to test for anomalies. So then when you get that new data point in, you say, does it match my model of the airspace? And it's a very simple program. We wrote the program, and we tested it out. And the nice thing about it is that you can also classify these anomalies. So the idea is, you know, once you get that information, how do you know whether it's maybe a hobbyist that flew out of their, you know, zone, or whether it's maybe an aircraft that's not responding, and it's not you know, cooperative, or, you know, could it be any other reason, right? So the idea is, how do we do this automatically? Well, if we have that model and then we have that data, we came up with a system that then can classify that. Based on simulations, we come up with different things. So we actually simulated what maybe a rogue aircraft would look like, what a hobbyist aircraft would look like, and we looked at all those trajectories, and then we trained a neural net to actually detect when is something wrong, and then is it what kind of anomaly is it. So here's a couple of the different flights we tested. So, you know, obviously these are, you know, conjured in a certain way so that we could test whether this works. We would need some real data to be able to do this sort of thing. But here we have, you know, the hobbyist type 1 that flies up kind of in a spiral, and then we have these other hobbyists, and we have the rogue types. Basically, the rogue types, they appear to be like normal aircraft, and you can see the blue and red lines up there. They're actually inside the lane system. but they're not conforming correctly, and they're not meeting some of the time constraints that that are expected. And so the system actually automatically classifies these and tells you which kind of aircraft it is. And really, we came up with a bunch of different measures for this, but you can tell. I mean, just if we were to post this on a screen, this type of measure, you would be able to tell right away that something is not right. So, here's one of those hobbyist aircraft compared to all of the other aircraft on the bottom on that right graph. And on the left graph, you kind of look, you can see, hey, there's something wrong with the blue lines. It doesn't look like the others. It's easy for us to tell. And if it's easy for us to tell that something doesn't look right on these graphs, it's also easy for a computer to tell. Like I said, we came up with a very simple neural network to do this type of classification, and it had 99% accuracy on our simulations. Of course, we would need real data to look at that, but we wanted to at least propose the system and say how it would work, and then when we finally have this Blade Runner type situation, we can actually test it out. So another thing that we looked at as part of this UTRAC project was cybersecurity, and we wanted to help UDOT Aeronautics understand what are the issues to consider. So when we go into these working groups and where we're discussing with industry, we ensure that we are getting the answers to the right questions and we're asking the right questions. So in terms of the attack landscape, there was actually a couple studies done. One of them was sponsored by NASA, and they divide the attacks up like this: and physical and cyber. Physical attacks that happen on physical infrastructure would be like disabling a cellular tower, or actually disabling vehicles. And really, the other end of the spectrum there is completely cyber attacks on non-physical hardware, which is like malware, viruses, figuring out where people are going using network traffic analysis and data theft and these sorts of things. So the question is, which ones should we worry about? Because really, there's no way to mitigate every possible cyber attack. In fact, that's an intractable problem. But what you can do is at least look at the different levels and say, what should we be most concerned about, and what should we deal with, and then what is the cost associated with that? So what NASA did was they looked at, what would be the cost to the attacker to actually do any of these types of attacks. And then they created a likelihood rank for those types of attacks. So the likelihood was really associated with the cost. So for example, if you had these what are called zero-day exploits or multilateral stage attacks, these are usually government-controlled, government-sponsored type of attacks. Someone is actively looking for a way to exploit a system, and that can be fairly expensive to do. And so, maybe we don't consider those at least in the short term, or we let the big players worry about them. Doing some sort of hack on the mission planning, maybe figuring out like I'm going to send out a fleet of robots to disrupt this system. Maybe a little more probable, but still improbable, because it would probably cost in the range of 1 to 10 million. Really, the ones that we want to worry about are the ones that cost little to no cash, or maybe a couple $1,000s. Usually these are in terms of ransomware and phishing and things like that. So really, and you can see in our paper, we look at some of the solutions, some of the possible mitigation measures to look at there. But it really is a matter of designing a system to keep these things out. So it's got to be a bottom-up kind of control there. So a little bit of the conclusion here. So where is FAA and NASA now? So I mentioned that I played a part in the AAM national campaign That was the X3 simulation, airspace simulation study. It happened over 2019, 2020, and 2021. And after that, there were a couple of the players as part of that went on to the next phase, which was the X4 simulations. And this included, companies like Uber. I think GE dropped out, and Google X-Wing, and these types of larger players. And some of the and they actually were testing things with real aircraft as well. And the question, I talked to one of the systems engineers at NASA and asked them, when are you going to publish stuff? We want to read about what you're doing. It sounds like maybe at the end of this year they're going to publish the results of that, but we can already see what they're thinking. They publish, at least from the software perspective, they publish these interfaces that allow the aircraft coordination to happen, and they make those open source so and anybody can see how these aircraft are going to be talking to each other, and that is on a website called GitHub, and we can see what the interfaces they have. And there was a new one that popped up, and it's called the Airspace Structure Definition Service, the ASDS. And if you look at that, it is basically a definition of a corridor. I would say it's a proto lane-based system. They're going to get there eventually, but they're thinking about it for sure. They found some issues, I'm assuming, with the coordination of multiple aircraft, and seeing that, hey, this is not an efficient way to do this. We're really reserving a lot of airspace, and we want to be able to sequence aircraft through the same location many times. A lot of these aircraft are going to be going through the same location, just like an aircraft. So there had to be some sort of structure that is defined in there, and I think that's what they're trying to do there. It doesn't have the scheduling piece, the strategic deconfliction piece that we're talking about, and I don't know if they have done a full analysis on it. But we published all of our work. Tom and I wrote a book about it, so it's published there. So hopefully they will read it, but who knows? Where are we going with all of this? So we call the system that we designed the Utah Advanced Air Mobility Simulator. A lot of folks at UDOT have access to it. If you're looking to get access to it, happy to give it to you. It's it is a prototype system for collaborating on these types of problems. It has like a developer interface, so it allows you to program things in Python, and then it has a geospatial interface that allows you to do those simulations. A lot of them you saw here. Excuse me. Additionally, we've taken this, since there's not really much, I would say, like commercial viability in generating these airspaces at the moment. There will be, I believe, but at the moment it's difficult to see. There's no aircraft, autonomous aircraft flying over our heads every day. So what we did was we went to the Air Force and we said, hey, could you use something like this? And to our pleasant surprise, they were very interested. And in fact, we got a phase 1 tech transfer grant with them, and we actually moved on to a phase 2. Once we're at phase 3, that means that we are productized and it's ready to be deployed. And so we're very excited about this project. We've modified the system to allow the coordination of different types of assets. That's ground assets and air assets, and looking at things like, what you're seeing here is actually a simulation of artillery going through this lane system, so they can coordinate all sorts of things that go through this system. Some of the continuing research is in terms of what do the vehicles actually look like. So we're still learning about what the performance capabilities of these vehicles are, and then also looking at more about what happens when there's a contingency. How do you model a contingency? What should the software do when there is a contingency? And a lot of those questions are still kind of out there. As an example, I spent some time working on a program called Gray Eagle. This is kind of the Army version of the Predator drone. And there were many cases, as a systems engineer on that program, there were many cases where the communication system would just lose contact. and the pilot or operator, as they would call them, would have us come out there and try to figure out what's going on. So I'd sit there with the pilots, and we take our antenna and we go in this spiral and try and find, where's the aircraft. At this point, the aircraft is flying completely alone, autonomous. We think it's probably going around in a circle. That's hopefully what it's doing. But these situations are still not greatly handled. I mean, what are you supposed to do in those situations? And so that's really where I think this has to go, is to figure out exactly what do they need to do. Because if there's a lot of aircraft in the air, then doing what those aircraft were doing, which is just blindly following a circle, can cause a serious issue. So with that is my presentation. Thank you for joining, and I'll take any questions or comments you may have.
Yeah, thanks, David. That's an excellent presentation. Any Q&A out there? Jared, you went live. Do you want to say anything as the project champion?
I will say this is one of the projects that I'm probably most proud of, that we were able to pull David on and get two subsequent projects with him. David, I'm gonna pitch your book right here. This is actually the book that David and Tom wrote that came out of this UTRAC project. Probably not your take it to the beach and read, but definitely worth cruising through if you can understand the calculus. I will say this is something that UDOT has led out on, that the Division of Aeronautics has led out on, and when we showed this to NASA, I mean, it blew their minds. And when I showed this at the Future of Aviation Symposium at UC Berkeley last month, literally I had people come up to me from the FAA, from NASA, from consulting firms, and I heard verbatim, this is the most comprehensive simulation we've seen today. And so David, kudos to you on that. And I know that Lisa's been sending me a couple of texts via the Gmail chat, but if anybody has any questions for David, has any questions on advanced air mobility in general, we'd be happy to talk about those as well.
Hi, this is Andrea Guevara. I got on a little bit late, so I may have missed this, but I'm curious why we're not using vertical differences so much in avoiding conflict, like grade separation, comparing it to the roadway network.
Yeah, so we do use vertical distances. We design the networks to have multiple levels, so that aircraft can travel in different directions over the same area. I think there's still limited space even going up and down, right? And a lot of the aircraft are trying to get from one place to the other. So at some point they have to sequence into the same area. And so this doesn't preclude, utilizing all of the vertical airspace and having multiple levels that these aircraft can fly. In fact, the benefit is that you can now actually tell how many aircraft can you fit, given this type of vertical separation and this horizontal separation. So I think that's still part of it. It's still needed to be defined for these airspace structures.
Yeah, how much vertical space is there in the lane-based approach?
So I mean, we were only considering. So again, we don't have actual vehicle models. We are making a lot of assumptions about these models. So what we did was we used these what we call low order models. We took out a lot of the dynamics of the system, and we said, we'll be able to actually design these airspace structures to fit any type of performance model that you come up with. But for our simulations, we had the top level of the for the 2-lane network at 400 feet, and the other one was at 300 feet or so. At least that was over the flat area. That's AGL over flat residential areas. But we've looked at systems that we're looking at in higher up airspace and this sort of thing. At least for the Air Force, we're certainly looking at aircraft that would be flying both crewed and uncrewed aircraft flying much higher as well. And we're actually looking as well at satellite coordination. So maintaining some satellite communication contact over a given area and coordinating that access. So it's really more of a coordination framework with limited resources, whether that be airspace or road or communications.
Any other questions?
Hi, do you know whether does FAA intend to impose a uniform system nationwide, or will there be local variation in local communities?
I think that's still an open question about how local control will, if it will even happen. The uniform system that they're proposing, at least, is this one, which is a way for operators to coordinate with each other without having a central system to coordinate. But I think that we're going to need some sort of, say, local control. It doesn't make sense. It would be as if your residential streets were controlled by the FAA. It doesn't really make sense. There has to be some local input into how these systems function. And so I right now I don't think that they're considering that. Jared might actually know more about that than I do, because I know he's been maybe arguing with the FAA about it and trying to create policy around this aspect. But engineering wise, it makes more sense to me that we would have some local control over how these airspaces are defined.
Yeah, so David's absolutely correct. Local control is almost a necessity. Although in my discussions with the FAA, there will be a national standard based on performance. But then that trickles down to, California being a very large state with a lot of MPOs may hand that down to the MPO level. Utah will probably keep it at the state level. The Boston, Massachusetts, Hartford, Connecticut, New York, Newark area has an entirely different, will probably have an entirely different method of maintaining that system, because there's so much urban density right there between in the New England area, so very small states. So it's got to be different. It's going to be different from Maine to LA.
Mm-hmm.
Questions from anybody else? Okay, well, we've just about used up the time, but David, excellent presentation and really interesting research to follow. So congratulations on a great project.
Thank you. Thank you everyone for the support, and thank you for the questions. Really appreciate it.
Okay. Good job, David.
Yeah, nice
Thanks.
work. I guess we'll bring the presentation to a close. So thanks again, everyone.
Thank you, Bob. Thank you, David.
Bye-bye.
See you guys.